Great, thank you. Great, it sounds like the mic started working. Cool, so yeah, today I'm going to tell you what we can learn about the universe from its baby picture. But before I do that, I'm going to give you a brief history of the universe and talk a little bit about what cosmologists study. What do we study? We look at the origin, development, and ending of the universe. I, in particular, look at some of the earliest of these moments. So most scientists believe there was some version of a Big Bang. And after that, there was this period of exponentially accelerating expansion right after the Big Bang, known as inflation, and that's what I study. Then within the first microseconds, or 0.000001 seconds, protons begin to form. So the things that make up regular matter, like you and me, or like the table in front of you. Then at about 0.01 seconds, nuclear fusion begins. So hydrogen and helium and different elements begin to form. This continues until the universe is about 3 minutes old. And then all of our primordial abundance of all of these elements is set. Then we get to a time period known as the cosmic microwave background, or what I was calling it in the title, the baby picture of the universe, when the universe is about 380,000 years old. And we can't actually see any light from before this cosmic microwave background, or CMB, and in a moment I'm going to explain to you why. And then nothing really happens until the universe is about 200 million years old. And that's when the first stars and galaxies begin to form. And then we can fast forward to today when the universe is about 13.8 billion years. So the way to read this plot is on the x-axis, we have the time of the universe, and then the size of the cone is showing you kind of what the size of the universe was at these different time periods. Sometimes you'll see a different version of this, where all the early universe stuff is squished, and then they talk a lot more of the late time stuff. But as an early universe cosmologist, this is what I picture when I think of how our universe formed. Okay, so I said we can't see before this cosmic microwave background. And I'm going to try to explain why. Imagine you were at a party, and it was really busy, and you wanted to walk to the other side of this room. Well, that's going to be really difficult. You're probably going to hit into a bunch of people and get bounced around in all these different directions, and you probably will never actually make it to the other side of that room. But then, as the night goes on, the party dies down, it might look something more like this. For now, it's going to be really easy to get to the other side of that room. You probably won't hit into a single person on your way there. Well, this is kind of like the light particles are photons in the early universe. At early times, the universe was so hot and dense, there's all these protons and neutrons and electrons around, that these photons or light particles were bouncing into or scattering. And this continued to happen until the universe got just cold enough that neutral hydrogen and helium began to form. At this time, there is now enough room for these particles to stream towards us, or like in the party analogy, to be able to leave that room. And we can take a picture of the universe at this time, and that's our cosmic microwave background. Funnily enough, though, the cosmic microwave background, or CMB, was actually discovered by accident. So two engineers in 1964 at Bell Laboratories, Arno Penzias and Robert Wilson, were using this huge radio telescope to do satellite communication experiments and measure the Milky Way. But they had this extra signal that they couldn't explain. No matter where they pointed this telescope, they were seeing the same signal, so they realized it couldn't be from the galaxy. For a while, they thought, well, maybe it's actually due to the fact that there's a bunch of pigeons in the antenna, and there's a bunch of pigeon poop. So they got rid of the pigeons, they cleaned that all out, and they still were seeing this signal no matter where they were pointing their telescope. So they were just going to publish this as a small note in one of their papers, until one of their colleagues said, you should talk to Jim Peebles. He is about to publish a paper predicting our cosmic microwave background. So they did that and found out that's actually exactly what they were measuring. And this discovery was so significant, they got the 1978 Nobel Prize in Physics for it. Jim Peebles also got a Nobel Prize in Physics in 2019, not only for predicting the CMB, but also doing work on structure formation, looking at dark matter, and also really revolutionizing the field of cosmology, figuring out a way where we could take our data and connect it to our theories and make it actually a predictive science. Also, he's Canadian, which is pretty cool. He's from Winnipeg. And if anybody here is old enough to have used an analog television, you've also detected the CMB. About 1% of the static that you get when you go between channels is actually our cosmic microwave background. So I should probably show you what it looks like. But before I do that, I want you to first imagine the Earth. So we know the Earth is a sphere. It's three-dimensional. But if every time you wanted to get directions, you had to grab a globe, that would be extremely inconvenient. So we make a map of the Earth or a 2D projection of our 3D Earth to make a map. So like on a piece of paper or on the screen here. Well, when we're collecting data in all different directions and getting a sphere of data. Similar to making a map of the Earth, we can make a map of this data. So here is the actual data from the COBE mission of our cosmic microwave background. You probably noticed that everything is essentially the exact same temperature. Well, these light particles are at about negative 270 degrees Celsius. There's no structure here. They're actually so much the same temperature that it's the same up to 5 decimal places. And this is really weird. And I'm going to try to explain to you why. So why our CMB is so uniform. So imagine you were having a potluck and you invited 2 people over. And both of those people brought potato salad. Well, this is pretty weird. They had like hundreds of dishes to choose from, but you can probably just say that was a coincidence. But now imagine you invited 1,000 people and every single one of them brought potato salad. Not only did they all bring potato salad, they all brought the same amount up to 5 decimal places. So about 1.000001 kilograms of potato salad. Well, this can't possibly be a coincidence anymore. They must have all talked to each other before the party or been in contact and decided to play this hilarious prank where they all bring the exact same amount of potato salad. Well, this is just like our light particles in the early universe. They must have all been in contact at early times to be the same temperature at our CMB. But if you remember, I said the CMB is when the universe was about 380,000 years old. If you work out how far light could have traveled in that amount of time, and with the universe expanding normally with normal matter, that works out to only about degree patches on the sky that should be the same temperature as each other. But we see the entire sky for our CMB being the same temperature, which means there must have been something that allowed everything to have been in contact at early times and still be the same temperature at our CMB. And that is one of our main motivations for inflation. So if you remember this history of the universe plot, we have inflation, which is causing the universe, instead of expanding normally, like you can kind of see with the rest of this cone, we have a period where it expands extremely fast. And the amount in which it expanded actually made it such that this tiny area of space was blown up so much that everything at our cosmic microwave background was able to be the same temperature. They were all in contact before. But we have to consider physics of the small scales, or quantum mechanics. Quantum mechanics says nothing can be perfect. There must be some small amount of randomness. So we shouldn't measure everything exactly the same. We should see tiny temperature changes. And we actually were able to measure this. Here's a map from the Planck collaboration of our cosmic microwave background with that average temperature taken away. And you can see all these tiny temperature changes on the order of microcelsius, or 0.000001 degrees Celsius. This might seem pretty insignificant, but these tiny changes in temperature and density is actually what caused our large-scale structures and galaxies to form. So these tiny quantum mechanical fluctuations being blown up to these super large astrophysical scales is the whole reason we even have galaxies in our universe in the first place, which is pretty cool. To your eye, though, this might not look super useful. There's not really many patterns that you can see. So what we do is we use computers and we take these maps and we make something known as our angular power spectrum. You can kind of think of it like taking a line and looking at both ends of this line and figuring out how likely is it that these 2 points have the same temperature. You can move that line and check these 2 points and move it again until you've covered every combination of points on this map. You can then try a different line size and check how likely it is these have the same temperature and move it around your whole map. Try different line sizes until you've tried all line sizes and done it across your entire map. And then you can make your angular power spectrum. There's a lot going on here, so I'm going to explain it piece by piece. So we have on our x-axis our line sizes, with the largest line sizes on the left to smaller line sizes on the right. And then you have your temperature changes on the y-axis here. This flat line corresponds to if all of the fluctuations were truly random. But this wiggly line is actually pretty close to what we measure with our data. So that's what we actually see in our universe. On the top, you can see little panels of what the CMB would look like at these different scales. So here we have 90 degrees, and we can see what we actually would see versus if there was truly random fluctuations. We then have 1 degree in the middle, and then 0.25 degrees on the right. So yeah, even though this looks just kind of like a wiggle, this is how we're able to figure out like what our universe is made of and a lot about its history. But light doesn't only have temperature, it also has electric and magnetic fields. So if you have a light particle traveling, it has a magnetic field and electric field that have to be perpendicular or 90 degrees apart. But they don't have to be up and down like this. As long as the magnetic and electric fields are 90 degrees apart, they can be oriented in any direction. That orientation is known as your polarization of your light. So imagine you had some light source that was emitting like vertical and horizontally polarized lights. And then you have a filter, or in this case, like a picket fence with these vertical slits, that's only going to let this vertically polarized light come through. Well, you've used this concept in your day-to-day life if you've ever used polarized sunglasses. We have the sun, which emits unpolarized light, which just means light of all polarizations. It can then scatter off of things like water. And when light scatters off of water, it causes horizontally polarized light. We then would have like 2 little vertical picket fences for our polarized sunglasses that block off all of this horizontal polarization and only allow in the vertically polarized light. It's actually really useful for us because horizontally polarized light is glare, and that's really hard on your eyes. So just like how polarized sunglasses work, that's kind of like how our telescopes work. We can imagine that we would have light from the Big Bang, or our CMB, and it will be traveling towards us, and it can scatter off of things like electrons, similar to how the light can scatter off of water. Then our detectors are kind of like having a horizontal picket fence and a vertical picket fence. So you can measure how much horizontally polarized light we have and how much vertically polarized light we have. But not only can things like electrons cause this polarization, so can gravitational waves and gravitational lensing. So here we can see a grid of space with different masses on it, where the larger the mass, the heavier it is. We can see for these heavier masses, it's causing this grid of space to become more deformed and cause a deeper well. Then the lighter masses, not as much. But, we live in 3D space and not everything is just stationary. So we can kind of think of it like this, where we have this grid of space and we have a moving source in there that's causing the deformation of space to change as it's moving around. You might have heard of gravitational waves being detected from things like neutron stars or black holes merging. So you can kind of think of that like you have your 2 masses, and this is an artist's rendition of 2 neutron stars orbiting each other. And those changes in space is causing these ripples to be emitted, or these gravitational waves. Kind of like if you threw a pebble into a pond and you have all these ripples. Well, in 2015, the Laser Interferometry Gravitational Wave Observatory, or LIGO, actually detected 2 black holes merging. And that was so significant, they got the 2017 Nobel Prize in Physics for it. And if you notice from what I was saying, the time periods between discovery and Nobel Prizes, usually it's like at least 10 years or more. This was so significant, it only took 2 years and they won a Nobel Prize. It was pretty crazy. Great, so yeah, we can have gravitational waves emitted. We also have gravitational lensing. So we have lots of things like galaxy clusters, are really big groups of galaxies in our universe. And we can imagine light being emitted from something like a galaxy. And as the light is traveling towards us on Earth, it's not going to go through this galaxy cluster. Space is being bent around it. So the light gets warped and lensed around a big galaxy cluster. Just like how this can happen with like galaxies, we have our CMB light that's being emitted. It has to travel through the entire universe to us. So it can get gravitationally lensed by things like these really big galaxy clusters. And we can actually measure this. So just like how the electrons can cause the polarization, we can have gravitational waves from the early universe. Inflation predicts gravitational waves would be produced. So that can cause polarization of our cosmic microwave background that we should be able to measure. And then we can also measure a signal from the fact that this cosmic microwave background, the light has to travel all the way to us and go through the whole universe. So that light will get gravitationally lensed, and we can measure the signal too. And I'm going to try to show you what that looks like. So the way that we talk about these types of polarizations in cosmology is E modes, which would be like up and down or left and right polarization, and B modes, which is offset by 45 degrees. But I said, we like to look in 2 dimensions. We like to look at the maps. So in 2 dimensions, these generalize kind of like to these cartoons on the screen here. Where on the left-hand side, you have these curled polarization patterns for our B modes. And the right-hand side are these divergent E mode polarization patterns. In our CMB maps, they kind of look like this, where the top panel is our E mode polarization, so all these diverging polarizations, and on the bottom is our B mode, so all these curled polarization patterns. But similar to our temperature, where we want to make a power spectrum, we can make a power spectrum of this polarization as well, be able to learn information from it. So now I'm going to show you the power spectrum, but with actual data, not just this cartoon version. So here we can see from a collection of telescopes, such as Planck, which I mentioned a little bit, and this is our temperature power spectrum. We have our E mode polarization power spectrum, and we have our B mode polarization power spectrum. The B modes, though, if you remember, I said have 2 parts. Part of it's from gravitational lensing, and part of it is from the early universe. Another thing to notice is that our error bars, or how uncertain we are on our measurements, are really small for temperature. We've measured that pretty well. They get larger for our E modes, and they're very big for our B modes. So current and upcoming CMB telescopes aren't targeting temperature as much anymore. We're looking at all of this polarization, trying to get our error bars as small as possible so we can figure out what our true model of the universe is. Okay, so now I'm going to show you how gravitational lensing and then how the amount of gravitational waves produced during inflation affects our B mode signal. So first, here's an example of our B mode polarization power spectrum just from gravitational lensing. So this is only the part that comes from this light being lensed on its way from the CMB to us. We now can add in inflationary gravitational waves, which will affect these largest line sizes or the largest scales. If we add in more gravitational waves, the amplitude for this thing will increase. And it will continue to increase as we're adding more and more gravitational waves. We do have very large error bars. So we don't know exactly which of these is true, but we can put an upper bound on how much gravitational waves could have been produced, because even with our error bars, we would have detected it if they existed. So this yellow shaded region is the current allowed area of our B mode power spectrum, or how much gravitational waves could have been produced during inflation. So that would mean things like these 2 darkest lines are ruled out. We would have detected that by now. But as you can see, there's a lot of lines that are still allowed within our data. Having no gravitational waves is actually still consistent with our data. So that's one of the biggest questions we're trying to answer right now with our newest telescopes, is trying to be able to measure this well enough that we can figure out which of these lines is the true model of our universe. Okay, but how can we actually measure these signals? Here is a little diagram breaking down the different things we have to consider. So we have our telescope, and then we have to consider things like instrument noise, the atmosphere if you're on the ground, our galaxy, this lensing signal, and all of this different stuff because the light comes from the CMB and travels towards us. And I'm going to go through each of these pieces one at a time. So on the screen is an artist and a rendition of one of the telescopes for the Simons Observatory, which we're currently building in Chile right now. And they have a type of detector which is known as a bolometer, which is a fancy way to say it measures a change in resistance with a change in temperature. Importantly, these are superconducting, which means that they're kept at this spot here where this tiniest change in temperature will cause a huge change in resistance. So if you had a light particle come in, it's going to heat up your detector, which is going to cause this little change in temperature, which causes this huge change in resistance. And we can measure that and figure out information about that light particle or that photon. But since they're so sensitive to temperature, you have to be really careful about the types of electronics that you connect to these things. Because if you have too much electronics that heat up, it's going to cause these to not work anymore because they won't be in their superconducting limit. And it wasn't until 1995, when there was technology developed to connect these detectors that didn't cause it to heat up as much because there were special electronics and they connected a bunch of the detectors together. So after that, in the early 2000s, we were able to start building these huge telescopes with thousands of these detectors because we didn't have this issue anymore because we weren't heating up the detectors as much, which is really what drove the field forward and really one of the only reasons we can do this type of what we call precision cosmology. Okay, so these detectors are measuring a signal over time. So an amplitude over time, and we call this a time series. We then can take these time series and we have to remove a lot of unwanted signals. So that includes detector noise, weird electronic malfunctions. You can have high energy particles or cosmic rays coming in and hitting your detectors. You can also have things like sources and maybe things like stellar flares. As you know, we have solar flares. Other stars do that too. And we can measure all of this in our data. And some of the things we want to get rid of, like electronic malfunctions and detector noise, but some of the things like sources we want to remove from our CMB data, but we want to still keep that data for folks that study those types of things because they can use this data. We don't want to just throw it away. Okay, so I'm going to talk a little bit about these sources. On the screen, you can see a video, which is extremely sped up, of the South Pole Telescope, and it's scanning the sky. You can see it's looking at one part in the sky, but it's going back and forth really fast, which means if there's a source there that it's measuring, it can measure if its amplitude is changing because it's going back and forth over it a lot. But what does it actually look like when it's measuring the source? Okay, so imagine we have a source. Our telescope is going to move across it. And as it's moving across it, each of the detectors, one after another, are going to see the source. So here you can see on the right-hand side, the focal plane or the detectors for the Atacama Cosmology Telescope in purple. And then in red is showing you the detectors that are seeing this source. This source in particular is Uranus. And then you can see the amplitude here on the left, where at each detector is starting to see it. Instead of it just seeing this kind of noisy pattern, it sees this spike in its amplitude. So that, has a pretty distinct look to it. We then can have things like the cosmic rays. Cosmic rays are going to come in, hit a cluster of detectors, and all affect our time series at the same time and have this one spike in the data. You can then have things like weird electronic malfunctions. Depending on what those are, they can look very different. This is an example, though, where you can see there's a striping pattern on the detectors. This is actually due to these special readout electronics you have to use to keep these detectors in its superconducting limit. But what happens is you connect a bunch of these detectors to the same electronics, which means if one of them has an issue, that signal will leak into the other detectors. It's something we call crosstalk. And that's something, we have to account for. But as you can see, all these things have pretty distinct patterns, which means we should be able to have a way to remove the signals we don't want and identify the signals that we care about. So one of the things that myself and actually Erica works on is we take these detector layouts and these different time series, and we have made a machine learning algorithm that can identify what are things we want to get rid of and what are things that are interesting and what are things we should send out alerts to folks to be able to then go and study, which is pretty cool. Okay, so we have other things we still have to care about. So for example, if it's on the ground, we have the atmosphere. A lot of these telescopes are built in places like the South Pole or Chile, which are very dry. So we have less of the atmosphere to worry about. And then usually they're built pretty high up, like on mountains. So you're above a lot of the atmosphere, but not all of it. So you still have to consider things like water. So water is H2O, or two hydrogens and one oxygen. Since it's not symmetric, it can get excited and rotate like this. When the water is rotating, it unfortunately emits light particles right in the wavelengths that we measure for CMB experiments. So here we can see wavelength on the x-axis and the strength of our signal on the y, where the color is corresponding to the amount of water vapor you have in the atmosphere. This data is from the Atacama Desert, which is the driest desert in the world, on a very high mountain where we build a lot of our telescopes. And this is still how strong the signal is that we have to remove. But it's not as simple as just removing a signal from all of the detectors at once, because our atmosphere is not uniform. Imagine if you had clouds. If you're looking not through the clouds, you're not going to see as much water vapor. Looking through different parts of the clouds, you'll see more or less water vapor. Also, it's not static. We have things like wind, which causes the clouds to move, which means you have to model this for the detectors independently, and then also how it's changing over time. So this can be difficult to remove, and that's part of why people like to send satellites to space, because then we can just ignore this atmosphere part altogether. But then there's other things we have to consider, like our galaxy and clustering and such. So I'm going to show this animation and kind of talk through what's happening at the different points. So this is an example for the Planck telescope. So Planck was sent to space, and then it scanned the sky to make this sphere of data that I was talking about. So you get this big sphere of data, and you can make your map of it. And you can see there's a lot of signals here, not just our CMB, and it measured 9 frequencies or at 9 different wavelengths. And there's a lot of work that goes into trying to remove these signals to be left with our cosmic microwave background. So this includes things like stellar cradles or nebulae where stars are born. We measure those in our maps. We also can trace out star formation in our galaxy by looking at the gas. We can actually see for some of them like pretty intense details of it, which makes this really, really useful for people that study things like star formation, because we can give them this data that we're collecting to use instead of just throwing it away. We can also see a lot of other galaxies outside of our own, like these galaxy clusters, which cause gravitational lensing. We can use this information to actually figure out how these galaxies are distributed in our universe, which, sometimes if you've seen a picture kind of like this, we call it the cosmic web, where we have a bunch of these little galaxy clusters, and galaxies are these really big bright spots. And we have to account for the fact that our light is being deformed as it's moving towards us through the cosmic web. So we have our cosmic web going back in time, and our CMB. These light particles or photons are going to be emitted. As they travel towards us, they will get lensed, and that will change our polarization. But we can measure this, and that means we can actually make a map of it. Oh yes, and here is showing you a CMB map and the tiny changes you get from this lensing. We can make a map of this cosmic web and this gravitational potential, which is pretty cool. Once we remove all of these signals, we are then left with our cosmic microwave background, which we can study to understand the early universe. So I had mentioned that Planck measures 9 frequency bands, or 9 wavelengths. And you can see here on the screen that at each of these wavelengths, different things are brighter. So for example, at 100 gigahertz, that's where our CMB is the brightest with respect to the other signals. But then, for example, at 857 gigahertz, all we can really see here is the dust of our galaxy. So we can measure all these different frequencies, and we know for all of these different components how their signal should change with frequency. Which means if we're measuring all of these different frequencies and we know how these signals should change with frequency, we can use that information to actually disentangle all of these different components and make maps of each of these individual things. So here are some of the component maps for the Planck telescope, where we can see the galaxy up here. We can see things like cold clumps of gas, galaxy clusters, magnetic fields, this gravitational lensing, or this cosmic web, and a lot more. So they're able to make all of these maps, and then folks that study all this different phenomena can use these maps for their work. And then for people that study cosmology, we're then left with our cosmic microwave background, which we can then make power spectra of, as I mentioned earlier. With this power spectra, we can then try to constrain models. So essentially what we do is we simulate a bunch of different expected signals from models and check if it's consistent with our data. Unlike a lot of science where you can do experiments to test a hypothesis, you can't really do that in astronomy. You can't do an experiment of a galaxy. So the closest we can do is do computer simulations. Say, based on this type of physics, this is the signal we expect. Does this signal match our data or not? So it's basically we have to infer all this information. So it becomes an inference problem. And I'm going to try to explain a little bit about how that works. So if you've ever seen Hell's Kitchen, one of the things that they do is the taste it, now make it challenge, where they're given a dish, they can see it and they can taste it, and then they have to try to recreate it with no other information. So figure out what ingredients it has, how much of each of these ingredients, from just being able to taste it. So this is kind of like if you were given a bunch of data with our error bars here, where you can immediately see some information. For example, here, that's probably not a soup. So you're not going to make a soup. We can immediately look at this and say, okay, this is probably a line. And if you remember what the equation for a line is, it's y equals mx plus b, where m is your slope, so your slope like this, and b is your y-intercept, so where it crosses this y-axis here. And similar to how you would then, try to figure out how much each ingredient you would need for it to taste the same, you can try making it and taste it. We can try different combinations of this slope and this y-intercept and see if it matches our data. So we can keep trying a bunch of these different combinations until we get one that fits pretty well. But the caveat is that we can't measure data perfectly. We have uncertainties in these different directions. So here, for example, is linear data that I made, and then I gave it some little changes or fluctuations. The plot I'm showing here in Coral, this line, is using the exact same slope and y-intercept I used to make this initial data before adding these tiny fluctuations on it. Even though it's the exact same underlying distribution, it doesn't 100% match the data. There's data fluctuating up and down and scattering around it. Well, that's just like when we measure data. We aren't fully certain on what it is. So there's going to be a bunch of different combinations of, for example, the slope and y-intercept that matches the data. Here's an example with a bunch of lighter versions of this coral line with different slopes and y-intercepts. And all of them match the data pretty well. So we can get a best guess and then how uncertain we are about that answer. So a distribution of possible combinations of slopes and y-intercepts that fit our data. And that's just what we do with the universe. We measure data, figure out what models match our data within the error bars. Okay, so what parts of this pipeline do I actually work on? So I do some of this removal of the unwanted signals. As I mentioned, I work a bit on the machine learning pipelines for low-level data, trying to detect things like electronic malfunctions to get rid of cosmic rays and sources. For example, for an upcoming telescope, that source finding is being implemented on it to be able to send out alerts to the community when we see a fast-changing source. I also work on things like estimating that crosstalk signal, so the leakage of signal between all these detectors. But then what I spend a lot of my time on and what I really love is doing more of this theory side, where I look at different models of inflation and predict what signals and do all these simulations that would be produced, and then compare it to data, figure out what signals we can rule out, which ones just don't match our universe, and which ones still match our universe, and how well we can constrain them. So there's actually a lot of telescopes that have looked for these types of things and are looking for it, but here's a not complete list with little purple stars on the telescopes that I work on. So there is things like WMAP, which was a telescope in space, Planck, which was a telescope in space, Polar Bear, which was a telescope in Chile, BICEP 2, which is a telescope in the South Pole. They have newer versions of this there now. The Atacama Cosmology Telescope, or ACT, which was a telescope in Chile. We're still analyzing the final data to get some more papers out, but we did tear it down, and in its place are building the Simons Observatory, which I have half in current and half in future because it's not done being built yet. Some of our detectors have looked at the sky and have what we call first light, but it's not science quality yet. We need to finish building the rest of it. Hopefully this year is the goal for this to start working for science. We have things like the South Pole Telescope, which is in the South Pole, CLASS, which is a telescope in Chile, and then other future things include LightBird, which is a satellite that should be launched in the early 2030s, and then PICO, which is another future telescope. So I've spent a lot of my PhD working on the Atacama Cosmology Telescope in the Simons Observatory, and then also LightBird, but I've actually been working on LightBird since in undergrad, actually. I did my undergrad thesis on it. So I think it'll be really cool. It's going to measure the largest line sizes, mostly for the B modes, to really drill down what happened in the early universe. The I here actually stands for inflationary. That's one of the main things it's looking for. Okay. So the takeaway for this talk is that we can measure this baby picture of the universe that is extremely uniform up to these super tiny changes in temperature. We can also measure the polarization of this light and those tiny changes too. We have to account for a lot of things along the way, like our gravitational lensing and galaxies and the atmosphere and things like that. But if we're careful enough when we're doing that, we can get good enough data to then try to constrain different models. So for example, we can use this data from upcoming telescopes and even some current telescopes to try to figure out how much gravitational waves could have been produced during inflation, which is a really important question to answer because we know our model of physics is not complete. And if we can figure out what happened in these earliest moments when the universe was so hot at these highest energy scales, it'll actually help us understand more of our complete model of physics and be able to figure out why the universe formed the way that it did and how it did it, and actually possibly how it's going to end, which is pretty cool, I think. But yeah, thank you. I can take any questions.
Okay, we have about 10 minutes for questions. Yeah, raise your hand if you'd like to ask a question.
Okay. Yep. Oh, thanks.
Idea sets that plank got. Yeah. How did you figure that out?
Okay, so if I'm understanding your question correctly, you're asking how do you go from these 9 different maps and figure out what the different parts are. So for example, like what the gas is, what the CMB is, things like that. Yeah, great question. So the reason that they measure all of these frequency bands is because different things are the highest signal in these different maps. Which means, for example, here at this high frequency, you can assume this map is what we call dominated by the dust. That's the strongest signal. There's other components. The CMB, for example, I know is 90 gigahertz, so around 100 gigahertz for its brightest. I think things like fast spinning electrons or synchrotron, I believe, is at the lower frequencies. That's where that's brightest. So we can use that information, and usually they will also use data from other telescopes that measure higher and lower frequencies. And then we can make a different type of spectrum, which is called an SED, or spectral energy density, which essentially says it shows you how each of these signals should change with frequency. So if we can measure what the dust looks like in its brightest channel, we can then kind of calibrate it to the other channels, knowing how much dimmer the signal should be. And we can use that, and we know that relationship for all of these different components, and we can use that to essentially estimate the brightness of the signal in all these different spots to be able to pull them out. Did that end? Okay, great. Yep. Yeah.
So you were saying that you're comparing the data to see if it matches what a galaxy looks like. But if it doesn't match the galaxy, what could they do?
Yeah. So your question is, okay, so if you have some data and you think some model's correct and you try to compare it and then it's not correct, like how do you figure out where to go next? Was that your question, or?
Be something like, would it be like something that's not a galaxy, or what's the galaxy there?
Okay, so how can we figure out if we have an incorrect model, or if we're using like the wrong parameters in it, or we haven't cleaned our data enough to be able to see that signal? Okay, so yeah, that's a great question. That's actually a lot of hot topics in Astro right now is about that. What things are being measured correctly and what things are systematics or issues with your data that you haven't fully cleaned out yet. In terms of things that look nothing like it, those you can probably rule out. But in terms of things that look really similar to it, and you have to really go back on your data and see, really make sure you've accounted for every issue that could have happened with your telescope, everything between you and that telescope, combined with more data sets, and also check other models, see if they fit better. But then another really, really important thing you need to do is look at independent measurements. So completely different telescopes and see what they measure. If they're seeing the same signal, it's a lot less likely that it's going to be an issue with your telescope, and more likely it's an issue with your model. And that actually leads to a lot of the open questions, like for example, measuring how much our universe is expanding. Early universe probes like the CMB measure one value for that. Close late time probes, so things like measuring things near us, like galaxies near us, get a different value. There's a really big debate right now of, is one of these values right? Is one type of instrument not accounting for its systematics correctly? Is both happening? Or do we not know our whole model of the universe? So we aren't actually modeling it properly. And the way scientists are trying to deal with that is really going through and using more advanced statistical methods to account for detector issues, but also building more telescopes to get more different independent measurements. So it actually is like a really big problem that we face. Did that answer your question? Okay, great. Yeah. Okay, so your question is, at what point in the timeline did subatomic particles form? Great. So that happened within after inflation and a microsecond. So if I go back to one of these history, the universe plots. Almost there, I think. Oh my goodness. Okay. Cool. Here. Okay. So subatomic particles, are the little things that would then make up stuff like protons and things, and then protons and neutrons can make things like atoms. So things smaller than protons formed between 10 to the negative 33 or 0 point at 33 zeros and then a 1 second and 1 microsecond or 0.000001 seconds. So within that tiny period, you go from a bunch of stuff which we don't actually understand with our current model of physics to making up the tiny things like quarks that will then make up things like our protons and neutrons. And then within that first microsecond, we then have all of our protons and neutrons and all of that have formed. Oh, yeah.
Wonder what is the highest number of frequency any telescope has measured and what kinds of things are you thinking of?
Yeah, so the question is, Planck measured 9 frequencies. What's the largest number a telescope has measured, and what types of things are they measuring? So I don't know the answer for all different types of telescopes or other fields of astronomy, but for cosmology, unlike CMB, I believe Planck measured the most. I'm pretty sure Planck currently has measured the most frequency bands. The upcoming Simons Observatory, if I'm remembering correctly, is going to be measuring 8 frequency bands, so it's actually a little bit less. But the future telescope, LightBird, is going to be measuring 15 frequency bands, which is really difficult to do, and it's using a special type of detector. So we can have, a lot of our detectors can measure 2 frequencies each. So if you want to measure a bunch of frequencies, you have to have a bunch of different detectors that can then measure 2 different frequencies. The way LightBird's getting around it is it's a new technology where you can measure 3 frequencies if you digitize it correctly, the data. And the reason LightBird is doing that is because if you've heard of, well, as you heard me say BICEP, but if you remember back in, I believe it was 2015, BICEP made a big announcement that they measured these gravitational waves from the early universe. But it was actually because they were using one frequency band and then trying to combine with some other experiments without correctly accounting for their systematics. They were actually trying to use Planck maps, but the not official Planck maps, so not the actual official data, which meant that they didn't remove the dust properly. And the dust can look like the gravitational waves. So that resulted in them claiming that they measured this and then retracting it 6 months later. And that's why other telescopes now are trying to be a lot more careful. And that's why LightBird, for example, because it's specifically trying to measure these gravitational waves, is measuring 15 frequency bands. And unlike Planck, for example, where there is a bit of a gap between each frequency, LightBird is overlapping in its frequency bands. So then we can really make sure we know 100% how that SED or how the amplitude is changing, how that actually is happening. So we can try to do as much of that like dust removal as possible ourselves. Did that answer your question? Great. Oh, yeah? Sorry, could you please repeat that? I couldn't really hear you. Okay, so let's see if I heard you. So I think you asked, can you measure the cosmic microwave background and other things like stars at the same time?
Black hole and a star core at the same time.
Okay, so can you measure the cosmic microwave background, a black hole, and a star at the same time? Yeah, so if those things are all like in the same point in space, you would be measuring it. Black holes themselves don't really emit things that we can measure as well with CMB telescopes, but they do make the different matter and stuff around it move really, really fast and ejects it, which is called AGN, which is actually one of the things Erica looks at. And we do measure that at the same time as our stars and our cosmic microwave background when they're in the same part of the sky as each other. So we can measure all these things. And then using these different like frequencies and wavelengths, we can then pull apart those signals to look at each of the individual components. So look at the black holes or the active black nuclei, look at the stars, look at the CMB all separately, even if they're measured at the same time. Okay, great. Oh, yeah. Sorry, after the cosmic microwave background. Between galaxies and today, or between CMB and galaxies? Here? Okay, so this is called the cosmic dark ages. And because, so if you remember for the CMB, I had said that hydrogen and helium was able to combine with electrons to make neutral hydrogen and helium, which meant the universe, on average, was neutral. We had to have a lot of that matter, which this is a huge open part of astronomy right now that people are trying to measure and some telescopes are trying to measure. We don't actually know this number exactly. We have a pretty big error bar on it. And once like all of this matter and stuff starts coming together and starts combining and gravitationally collapsing, it can then form our first stars. That time period is known as reionization. And we don't actually know 100% how that happened because all the stars we see today are called population 1 stars. Then if we go back a little bit in time, and then some of our older stars we have are called population 2, then this would be population 3. We have a pretty good idea how population 1 and 2 formed. It's still not super certain how these population 3 stars formed in reionization. So we know the basics of we have a bunch of gas, neutral gas, it starts combining, which then will create stars, which has nuclear fusion and things like that. That will then cause the universe to ionize because you're heating it up. So these electrons will come off of our neutral atoms, but we don't actually know 100% how that happened. That's one of the things the Simons Observatory is going to be looking at. And things like JWST is trying to look back at reionization as well. That's one of his goals, yes. Other things it's looking at would be like exoplanets, so planets around stars that aren't our own. And that's one of the things I'm sure Michael will talk about because that's what he studies. Yeah. Cool. Yep.
Thank you for your public lecture this evening. You'll have to forgive me if I miss this point. So you're measuring the cosmic microwave background. Does that have a distinct signature compared to other objects that might be in the solar system right now that can also give off a microwave signal? How do you distinguish between them?
Yeah, so the question is, if I'm understanding that, how can we distinguish something like the cosmic microwave background to something else, maybe in our solar system or otherwise, that's also emitting microwaves? So one of the biggest things that we have for the CMB is that no matter where we look in Earth, in the universe, the CMB looks the same in all directions. It is the same in all directions and no matter where you go. So If we're measuring a signal that doesn't change no matter where we're going, we can be more confident it's the CMB, versus if we see a signal that's only coming from one direction when you're looking at it. A kind of infamous example is there was a telescope that had a microwave in its break room that wasn't correctly containing the microwaves, and they noticed they were getting this weird spike in signal at lunch every day. And they microwave actually emitting these, but they could tell it couldn't have been the actual signal because they were seeing it at the same time from the same area. So yeah, we can use that type of information to figure it out.
That microwave background is fairly static, if you will, that you could map it to today's world and it would look essentially the same.
Yes. Yeah. Yes. Yeah, it'll look the same for us at no matter when we're measuring it and where we're measuring it.
So like a
Yeah.
road map change much. That's
Yeah, exactly. And like there are small changes between like, you know, if we measure it from the northern hemisphere and the southern hemisphere, but that's just because, you know, on statistically everything's like the same on large scales. But yeah, it'll look the same no matter. And that's why we can combine data from different experiments. Cool, yeah, no problem. Okay, cool. Yeah.
Get rid of all the levels of dust in the atmosphere. And I was just curious if do you think computers would ever be able to do that, and it would actually be worth it to train a computer to do that?
Yeah, so the question is, you know, we have hundreds of people trying to do things like removing these signals like dust. Do I think it would be worth it to train computers to do this or to take over some of the work? Was that your question? Oh, yeah, sorry. How long it would take to get computers to do that? Okay, so we actually currently use computers to do, you can't do astronomy anymore without a computer. We have way too much data. So the way that we use computers, and we can use things like, you know, fancy machine learning algorithms and different things like that, is we can give it data, you know, that we know, and we know what the signal should look like. And as you were saying, you know, you can train a computer to do some of that work for you. So you can train a computer to try to remove these signals. And there is a lot of work being done right now. There is no full CMB pipeline done via things like machine learning, but different components are starting to move more towards that. It isn't perfect, but also people aren't perfect. So a lot of what's happening is it's people making these different algorithms to do parts of it, but then they're still kind of, you know, like sanity checking as they're going and making sure that things are working well. And so like checking as things are going. So I think like when it comes to probably not this next set of CMB telescopes, but maybe after this next set, we're starting to develop a lot of these algorithms. Because even though, you know, computer science has all this stuff, we didn't have it, we didn't always use it, right? And we're trying to implement it and kind of test it. So by the next set, it'll probably be more automated, but you still will need people there to be able to like check that it's working and also to do the actual analysis and like physical interpretation of what's happening. And that would free up a lot, like for example, all the pipeline stuff I do takes away from all my time to do the science that I love. Being able to have computers do the stuff that is more like not really what you're interested in is great, because then you have time to actually think about new ideas and think about new theories and such. Yeah, so I think maybe the next generation would have more of it, was the answer.